All right, so getting into section 2 of chapter 4, we're going to get into the mean value theorem for derivatives. Now this is a very important theorem. You need to know what this is and you need to know how to use it. Let's just get right into it. The mean value theorem for derivatives says if f of x is continuous over the closed interval from a to b, that means the endpoints are included, and it's differentiable over the open interval from a to b, endpoints not included, then at some point c between a and b, f prime of c must equal f of b minus f of a all over b minus a. Now, hopefully you're recognizing this side over here. It's just the slope, which is also known as AROC, the average rate of change. This is the rate of change from one point to another. The average rate of change over that interval. Over here, we've got the derivative, which is the instantaneous rate of change. That means when we've got the curve, we're looking at the slope at one point only, the slope of the tangent line. So what we're looking at here, we're saying that if we have a function that's continuous and differentiable over an interval, then there's some value in that interval where the derivative, the instantaneous rate of change, is equal to the slope from one endpoint to the other, the average rate of change over the interval. That's all we're saying. That's all that this is. Now, we've talked about theorems before that were existence theorems. It tells you something exists, but it doesn't tell you how to find it. Such as in the last section, we talked about the extreme value theorem. It tells you that if a function is continuous over a closed interval, you're guaranteed an absolute maximum and an absolute minimum. It doesn't tell you how to find it, though. This one is more than an existence theorem. It actually has an equation built into it that you can use. And what we'll use here is this. Over some interval, we'll be looking for what c is. Where in that interval the derivative is equal to the average rate of change. That'll be typically what your problem is going to be. Now, the mean value theorem applies only over a closed interval with those endpoints included, because we're actually finding the average rate of change from the endpoint to the endpoint. And the mean value theorem says that at some point in that closed interval, the actual slope, the slope of the tangent line, equals the average slope. That's all this thing says. And we can use this equation right here to find out where the actual slope is equal to the average slope. We would first find the average slope value and then set the derivative equal to that and solve for x. Because your c value is nothing more than the x value where it occurs. That's all c is. Don't be thrown off by c. C is just an x value somewhere in the interval from a to b. But c is an x value where this thing is equal to this thing. So for instance, let's say we have our function here and we've got a here and b there. The slope of this chord or this secant line right here is f of b minus f of a over b minus a. F of b is the y value here at b. F of a is the y value here at point A. And then b minus a, of course, is self-explanatory. Nothing more than y2 minus y1 over x2 minus x1. Now, the tangent, we're looking for where this tangent of the line of this curve somewhere in between a and b is going to be parallel to that chord, because if the two chords are parallel, then the slopes are equal. So we're looking for where the slope of the tangent line is equal to the slope of the secant line. I don't like the word chord here. I'd much rather say secant line, because the secant line is from this point to that point. All right, now let's look at a couple of somewhat obvious definitions. A function is increasing over an interval if the derivative is always positive or 0. And I'll explain the or 0 here in just a second. And in the same way, a function is decreasing over an interval, and we're talking about over the entire interval, if the derivative is always negative or 0. Now, with the whole 0 thing, here's the case. Think about y equals x cubed. So if we look at its graph, it's going to start down here and come up, and it actually gets flat and has this derivative of 0 there in the middle and continues on. But we say that this thing increases over its entire domain. Even though at this one point right here at 0, it actually has a slope, otherwise known as a derivative, that equals 0. But we say it increases over its entire domain. So just because it gets flat for a point does not mean that it's not increasing for the entire interval. So it can actually flatten out. Now, if it flattens out for an extended period of time, the slope is 0 all the time, or for multiple points in a row, then it's not increasing over the whole interval. That's the difference between these two. So be careful about the or 0 part. Don't think that it can be that a horizontal line is increasing. A horizontal line is not. We're talking about just selected points there. This is actually increasing on the entire interval. Now, let's say you're asked, when is this thing increasing? Well, if you were to tell me that negative infinity up to 0, open interval, and then union that with 0 to infinity, would you get this thing wrong? If you say it's increasing, but you say it like that, where you actually do not, notice we're not including 0 in this, that would be completely right. It would be accepted by AP. So the whole thing about increasing at 0, or whether you include that 0 or not, it doesn't matter, because if you're including or don't include it, they would give you the credit. They would also give you the credit for negative infinity to infinity if you said that that's where it's increasing, because technically this is increasing for all values because of that 0 point. It's increasing on this side, it's increasing on that side. It just happens to be at one point where it doesn't. So you can either include the 0 in your interval or not include it. You're going to get it right for an interval either way. Just understand that that's the case with the 0. But it can't be an extended period. It can only be like the 1 point right here. If it's 0 for all the points, it's a horizontal line, which is neither increasing nor decreasing. It's a constant. So hope that cleared everything up as clear as mud. But that's the situation. Sometimes you're going to hear this referred to as increasing on its entire interval. Sometimes they'll say that it's increasing from a negative infinity to 0, the same way we were talking about it writing here. You're going to hear it referred to both ways, because it's almost like it's not really an opinion, but more of a taste, which one you prefer to the other one. And that's going to be what you're going to run into with your instructors as well. That's why AP gives credit both ways. Now, if we look at these two functions, they have the exact same slope at any value of x. So functions that have the exact same derivative differ only by a constant. So if I were to say, let's say this one up here is sine x plus 3, this one down here could be sine x plus 1. And that means that c is equal to 2. There's a difference in 2 in every one of these values. Now, it looks like some of these lines are longer. They're actually not. They're the same, because we're just talking about the vertical change. But both of these, if we took the derivative of sine x plus 3 and we took the derivative of sine x plus 1, what's our derivative going to be? Well, for each of these, the derivative is cosine. And that's what we're talking about here, because functions of the same derivative differ only by a constant. And why is that? Because when we take the derivative of this, what happens when we take the derivative of the plus 1? Well, the derivative of 1 is 0. But also, what do we know about 3? The derivative of 3 is 0. So these constants go away when we get to the derivative. So let's say we were asked, find the function f of x whose derivative is sine x and whose graph passes through the point 0,2. All right, so if we say the derivative is sine x, so we've got f prime of x equals sine x. What is f of x? Well, think backwards because we're actually doing a derivative in reverse. What function would I take the derivative of to get sine x? Well, if you take the derivative of sine x, you get cosine x. If you go backwards and say, what would I take the derivative of to get sine x? It's actually negative cosine x. Now, if you're having problems with that, remember the little trick I showed you. Sine x, cosine x, negative sine x, negative cosine x, and going this direction, we're taking the derivative. And then it wraps back around. Now, if we're going backwards, we would take the antiderivative, which we'll talk about in just a second, and we start here and we go opposite the way the arrows go, and that's where we get the negative cosine x. But don't forget the c. We have to put the plus c in here because it's going to be negative cosine x, but it could be anywhere up and down. So we actually would have to put the plus c because there may or may not have been a constant there. And the way we're going to find that is using this point right here. So the graph of the function passes through the point 0,2. That means that f of 0, which is equal to 2 here, has to equal negative cosine of 0 plus c. Now, what is cosine of 0? Well, cosine of 0 is 1. So we end up with negative 1 plus c. We're going to add 1 to both sides. So 3 equals c. So that means that up here, I can now take my function that I found, and I can actually write the specific solution to this is negative cosine x plus 3. So this is the solution of this problem right here. It's the function that if I take its derivative, it's sine x, and if I were to graph this thing right here, it's going to pass through the point 0,2. Now, you're always going to include the plus c when you do these, but you can only find c if you're given a point that's on the function. Then you plug in your x and you plug in your y, and you solve for whatever the c is. Now, this process of finding the original function from the derivative is so important that it has a name. It's called the antiderivative. A function capital F of x, by the way, capital F of x is the notation for an antiderivative of little f. So when you see the capital letters, that means that you're talking about an antiderivative. So the function capital F of x is an antiderivative of a function little f of x if capital F prime of x is equal to f of x for all x in the domain of f. What this means is if I take the antiderivative and the derivative of that, they cancel each other out, so that means that my function will be the same as what I would start off with. For all x in the domain of f, the process of finding an antiderivative is called anti-differentiation. Now, you're going to hear much more about antiderivatives in the future. This section is just an introduction, so you've seen it before. We're going to talk about those starting in chapter 5. Actually, more specifically in chapter 6, but we'll hit them. We'll start talking a little bit about them in chapter 5. All right, so let's do an example with that. For example, find the velocity and position equations for a downward acceleration of 9.8 meters per second squared and an initial velocity of 1 meters per second downward and an initial position of 36 meters high. Okay, I know you're looking at that and you're saying, holy crap, there's so much stuff that's thrown at me right there. The thing is, here's what you've got to understand. Acceleration, a of t, which by the way is what? The derivative of the velocity. And we know that it is 9.8 meters per second squared. Now, velocity, this part right here, will not come in until we do the antiderivative here. So let's get rid of our units for right now. And if we do the antiderivative of v prime, we're going to get v of t. And all you're going to do, you're going to use the power rule, but you're going to use it in reverse. Here we've got 0 as our power of t. So we have t to the 0, which of course is 1. This is understood to be there. We're going to increase that power to 1 and divide by that same power. So what is t to the first divided by t? Well, it's just t. So we end up with 9.8 t. Don't forget your plus c. All right, so then that's where our initial velocity here of 1 meters per second downward comes in. Oh, and by the way, this should be downward acceleration, so it should be negative 9.8. All right, so our initial velocity, so v of 0 equals 1 meters per second. And that means that t is 0 everywhere in this. So if we have negative 9.8 times 0 plus c, well, that just goes away. It's 0. So we end up with c equals 1. So now v of t equals negative 9 point, sorry, its initial velocity downward, so that should be a negative 1, 2. My negatives are messing me up here. I'm not paying attention. Minus 1. So there is the actual velocity function for this problem. All right, so we know that v of t, let me change colors here just so they don't run together. So v of t, as I've just found, is negative 9.8 t minus 1. And we want to find also the position equation. Well, remember, v of t is what? Let me back this off just a little bit. V of t is equal to s prime of t, where s is the position function. So we're going to take the antiderivative again and get s of t is equal to, we take the antiderivative of this, remember we're going to increase this power, which is 1, to 2, and divide by that. So negative 9.8 divided by 2 is negative 4.9. T squared, and do the same thing here with the negative 1 we did with the 9.8 here. That's just going to be minus t plus c. All right, power rule in reverse. Increase the power, divide by that number. Increase to 2, there's the t squared, and divide this thing. What we did here is we divided 9.8 by that 2 to get the negative 4.9. Over here, once again, we have the t to the 0 that we increased to the power of 1 divided by 1, so we get negative 1 t to the first power. And then the plus c anytime we take an antiderivative. Now, we have an initial condition or initial position of 36 meters high. That means that that is s of 0. So s of 0 equals 36, which equals this thing right here with 0 plugged in everywhere we got a t. Negative 4.9 times 0 squared minus 0 plus c. So c is 36. That gives me this equation right here, solved for everything, to be s of t equals negative 4.9 t squared minus t plus 36. So there is my velocity function. There is my position function. And that's how you would find those. Now, while we are going to talk a lot about these in future chapters, you do need to know how to do the simple ones like this for the test. You may see one.